We had 8 questions to do on page 168 for homework. We're going to take a look at question number 8 here. It says blocks X and Y are attached to each other by a light rope that can slide along a surface, horizontal frictionless surface. Blocks X has a mass of 10 kilograms, Y has a mass of 5 kilograms, and there's an applied force of 36 newtons to the right acting on block X. We want to find the action and reaction forces in the blocks exerted on each other. In other words, we want to find, we talked about this yesterday, we want to find an internal force. We want to find the force of tension in that rope that joins X and Y together. All right, we know what to do here, right? We know that we have to break this up into really 2 problems. We have to analyze the system of one object, pretend it's one object, at least X and Y together, find the acceleration of that system, and then once we have the acceleration, pick one object, either X or Y, and analyze that one object. So let's do the system first here. We say that, let's see here. We've got a free body diagram drawn already for, let's say that F net is equal to the sum of the forces. Looks like there is only one force acting here that's not unbalanced. It's the applied force. We say M times A is equal to the applied force. And the mass here is going to be, what do we have, 5 and 10? The mass is 15 kilograms times the acceleration equals the applied force of 36 newtons. (36 divided by 15 is 2. A is 2.4 meters per second squared. All right, there's the acceleration. Now we got to analyze one object or the other and find the use the acceleration that we just found to find the tension between the two, or the internal force between the two, or as they call it here, the action-reaction force between the two. Now I'm going to analyze object Y. Does anybody want to make a suggestion why I picked object Y, the 5 kilogram object? There's no really good reason why I had to pick object Y, but I picked it because it made it a little bit easier. How come it made it a little bit easier than object X? Yep. There's less forces. There's only one force acting on object Y, and that is the action-reaction force, the force of X on Y, which is what I'm looking for here. So we're going to say for that object, the net force is equal to the one force, that's Fxy, M times A, 5 times the acceleration of 2.4 equals Fxy. So 5 times 2.4 is 12? So Fxy ends up being equal to 12 newtons. All right? Does that make sense? If we pull on this with 36 newtons, a system with 36 newtons, then Fxy is going to be less than that? Anybody tell me why it's going to be less than that? Why could I not possibly get a number that's bigger than 36? If 36 newtons is enough to pull the entire system, accelerating it at 2.4 meters per second squared, then you certainly don't need 36 to accelerate 5 kilograms at the same rate of acceleration. So it's going to require less force to pull this guy at 2.4 than it is to pull the whole thing at 2.4. Of course we're going to get a smaller force, right? And you know what? If you take a closer look at this, it's proportional to the masses. Do we need 36 newtons to pull the entire thing? How much do we need to pull 1/3 of the mass? Lo and behold, it's 1/3 of the force to pull 1/3 of the mass, right? Not a coincidence, it ends up being 1/3. Okay, question B says, suppose the magnitudes of the force of friction on X and Y are 8 newtons and 4 newtons respectively. What's the action-reaction forces now? All right, I'm going to erase that and go back to drawing a free body diagram here for this. X is, we'll call this FFX is 8 newtons, and we'll call this FFY, that's going to be 4 newtons. We got to analyze the system to find the acceleration of the system. It's going to be different now that there's friction. It's going to be FFY plus FFX plus F applied. The mass here is 15 kilograms again times the acceleration. We can't assume it's 2.4 again because now there's friction. the situation has changed. FFy is -4, FFx is 8, F applied is 36. I think we get 2.6667 meters per second squared there when we do that. Agree? All right, now let's analyze one object. Let's pick object Y again, I guess. Object Y has a mass of 5 kilograms. It is a force to the right. That's going to be the action-reaction force. We're going to call that Fxy. It has a force to the left acting on it, and that's going to be Ffy, and that value is 4 newtons. So we're going to say the net force is equal to the sum of the forces. We're going to say 5 times 2.667 equals, what do we get? Fxy plus Ffy is -4. Solve for Fxy, I think it works out to be 17 newtons. Why is that force bigger than it was the first time? Just because I added friction, why is the force bigger? Well, I have to pull the same mass. I have to pull 5 kilograms, but now I have to pull 5 kilograms when it's being pulled back the other way by something like friction. Okay, if you're in a little tug of war and you've got one person pulling against you, you have to pull with a certain force to accelerate that rope in your direction. If you've got 5 people pulling against you, then you have to pull harder in order to pull against that rope and against those 5 people that are pulling in the opposite direction. When you have more force pulling in the opposite direction, not only do you have to move the mass, the 5 kilogram mass, but you have to overcome that force that they're pulling back on the other way. Okay, we have more force pulling back the other way in this question, therefore we have to pull harder. 17 newtons has got to be a bigger force. Right? All right. I would like you to have a look at this question, please, on the board. See what you can do with that over the next 4 minutes or so, please. All right. What's the first step in solving this problem? External forces, right? We got to analyze the system with the external forces. We're going to pretend that this is one object. Okay, it's a wagon with 2 people in it, or it's a semi-truck with a whole bunch of crates in it, or whatever the case may be. It doesn't matter what the individual people inside or the individual objects inside weigh. What matters is the total mass of the system. So the total mass of the system in this case is 28 kilograms. We've got a Freebody diagram drawn already. Everything except the force of gravity, the normal force. It's really okay that we leave those out this time because they cancel each other out anyways. All right, let's find the acceleration of that system by analyzing the entire system here. We're going to say the net force is the sum of the forces. That's going to be FF1, we'll say, plus FA, plus FF2, plus F. It looks like we have 2 FAs. FA1, we'll call it FA2 to the right. All right, the total mass is 28 kilograms times the acceleration. FF1 is -18 plus -18 plus -27 plus +85. We do the math there. What do we end up getting for the acceleration here? You got that, Natalie? You got that one? 0.786. Do you agree with that? Yes. Thank you. 0.786 meters per second squared. There's the acceleration of the system. There's the acceleration of object 1. There's the acceleration of object 2. Now, if we want to find the tension in the rope between the two, we're looking for an internal force. We're looking for an internal force. We're going to analyze one object. Which object do you want to pick here? I don't think it really matters this time. I think we have 3 forces acting on both of them, so pick one. Usually it seems like we go with the one on the left. Let's pick the one on the right this time. We have an 18 kilogram object. How many people picked the one on the right, by the way, the 18? Okay, how many people picked the other one, the 10? Okay, about 50-50. That's fine. Doesn't matter. Okay, the only difference is the direction of the force we're going to get. Okay, I'm going to end up getting a negative force. If you pick the other object, you're going to end up getting a positive force. Should be the same value, though. We have FA here. It's 85 newtons. We have FF of 27 newtons. And then we have this force of tension that acts back this way. We'll call that the force of 1 on 2, which is really what we're looking for here. We're going to say F net is equal to the sum of the forces, F12 plus FF plus FA. Notice I'm putting all these in as positives. I always do when I'm writing out this step, because F net is defined as the sum of all the forces, adding all the forces together. It's the next step where we put in negative values, when we sub in numbers. M times A, the acceleration we know is 0.786. We're going to go with the same value we had, because in the end, if the whole system accelerates at that rate, so does the 18 kilogram mass inside. F12 is what we're looking for. FF is negative 27. FA is positive 85. 18 times 0.786, subtract 85 plus 27 ends up giving me what? So I need to have that one? 3.4? 34.86. Anybody agree with that? Oh, okay. 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 Fair enough. Yeah. Negative 43.856. So that would be negative 44. Just two significant figures. Anybody agree with that one? Yes? No? Yes? Negative 44 newtons. All right. There we go. All right. Good question. You guys are, I think, on the right track on these. If you missed a force, hey, that's okay, as long as you understand why that force is important. Okay, next time nail it, and we're okay. So look at our worksheet now. We had 4 questions on this worksheet. Both, or all 4 of them, elevator problems. I want to do a couple of those questions. Let's do question number 2, and let's do question number 3. 2 and 3. 2 says calculate the force of the floor pushing up on the person in the elevator. What are we really looking for here? The force of the floor pushing up? What's another name for that? Yep. Good. The normal force. We could also call it the force of the floor. You could also call it the apparent weight, the perceived weight. It's how heavy we really feel, right? It's not how heavy we are. That's the actual weight, the force of gravity, m times g. But it is how heavy we feel. All right, let's draw that free body diagram. We're going to say gravity is acting down, and we're going to say the normal force acts up. But which is going to be bigger, gravity or the normal force here? How long do I draw that normal force? How long do I draw that normal force? Tori, how long am I going to draw? Bigger or smaller than the force of gravity? I'm sorry? Why am I going to draw it bigger here? Because I'm, sorry? Question number 2. Good. You're accelerating downwards. It's a downward acceleration, so we're going to make that a smaller normal force than force of gravity. Let's think logically about that. If we have a downward acceleration, then the net force has to be downward. Therefore, the force going downward has to be bigger than the force going upward. All right, let's set this up the same way as we set up the rest of them. F net is equal to the sum of the forces. That's Fg plus Fn. And we're going to say m times a is the sum of the forces. 50 times negative 2 is equal to 50 times 9.81, but we got to make this negative. I don't care whether you put the negative in front of the 5, the 50, or in front of the negative, in front of the 9.81. Doesn't matter, but you need a negative in that term. Add that to the normal force here. 50 times negative 2 is negative 100. This is negative 490.5. We're going to take the 490.5 over by adding, and we get 390.5. We should round that to 3 digits, or 391 newtons. How many people got that? Is there a mistake there? I just saw a hand up before. Mistake? How many people got that? Okay, good. 3 says calculate the apparent weight of the person in the elevator. What are we really looking for there? What are we trying to find here? The apparent weight? What variable is it? Ravi, what variable are we trying to find here? Yeah, we're looking for the normal force. So let's draw the free body diagram again. Understanding we're looking for the normal force. Fg is downward. Fn is upward. How big is Fn? Same value? Bigger? Smaller? How big is it? relative to the force of gravity here. Yep. Yeah, we're going to make it the same because it's constant velocity. Remember, when it's constant velocity, we're in translational equilibrium. And when we're in translational equilibrium, we have to have balanced forces. Both of those forces have to be the same. So let's set it up the way we always do. F net is equal to the sum of the forces, Fg plus Fn. And we're going to say m times a, 65 times, what's the acceleration here? Yep. Good, 0. The acceleration is 0 because it's a constant velocity. What if the constant velocity was 25 meters per second downward? The acceleration would still be 0, right? This problem wouldn't change. Think about that. You're in an elevator moving upward at 3 meters per second. You're in an elevator moving downward at 25 meters per second. You don't feel a difference. It feels exactly the same to you. As long as there's a constant velocity, it doesn't feel any different. It's acceleration that you feel, right? Not constant velocity. All right, the force of gravity is negative 490.5. That's 50 times 9.81 plus Fn. 0 is equal to negative 490.5. So Fn ends up being equal to positive 490.5. So there we go. How heavy am I really here? 490.5. How heavy do I feel? 490.5. So my apparent weight is the same as my actual weight, regardless of how fast I'm moving. That's why you wouldn't even know if I'm moving upwards or downwards or at what speed. Did I make a mistake there? Oh, sorry, my maths. Yeah, you're right. The mass is 65 times 9.81. Tried to take a shortcut there, and that's what happens when you try to take a shortcut, I guess, right? 65 times 9.81. What does that equal, Emma? Okay, so we're going to solve for this, and it works out to be 637 newtons for Fn there. My force of gravity is negative 737. My actual weight, my apparent weight is positive 637. I feel the same weight as I really am, regardless of whether I'm stopped with a 0 acceleration or moving at a constant velocity of 3 with 0 acceleration or moving at a constant velocity of 25 with 0 acceleration. I would feel exactly the same way. You guys comfortable with that? All right. Here's another multi-force problem that looks completely different, but you're going to see in just a few minutes that it's not all that different. So it says a 20 kilogram truck tire, object A, is lying on a horizontal frictionless surface. The tire is attached to 2 light ropes that pass over a light frictionless pulleys. The hanging pails B and C, B has a mass of 8 kilograms, C has a mass of 6 kilograms. We want to find out the acceleration, the magnitude of the acceleration. Can you tell me which way it's going to accelerate before I even start this question? Is it going to go left or right, this 20 kilogram tire A? Left or right? Who says left? Who says it's going to go to the left? Who says it's going to go to the right? Why is it going to go to the right? Why is it going to go to the left, anyone? Yeah, it's going to go to the left because pail B is heavier. Right? If you pull on something to the left with a bigger force than you pull on it to the right, it's going to move to the left. Now, let's start drawing a free body diagram here. We have a force of gravity acting down and a normal force acting up on the tire, but they cancel. So just like in all those other problems, we're not going to worry too much about that. The only other 2 forces we have acting here are the force of gravity acting on B. I'll call that FB, and the force of gravity acting on pail C. I'm going to make that a slightly smaller force because the mass is a little bit smaller. So we set this up. We say F net is equal to the sum of the forces. That's going to be FB plus FC, which are both forces of gravity. F net is m times a. The mass, by the way, is the mass of the entire system, just like it was in those other problems we did with multiple objects. The mass of the system, 8 plus 20 plus 6 is 34. FB is, it would be 8 times 9.81, right? And FC is 6 times 9.81. Should we make those both negative because they're acting down? Is that right? Should I do that? I'm not saying I should. I'm asking you. Should I make those both negative because they're acting down? Okay, I see a few people nodding. A couple people nodding there. Here's the deal. The reason this question is a little bit different than questions that we've done before is because we got a problem here with our signs. We had them both positive. Well, we changed them to both negative because they were both acting down. Shouldn't really matter if they're both the same sign, whether we make them negative or positive. But the problem is they're not both the same sign here. One of them is negative and one of them is positive. Despite the fact that they're both down, one is neg and one is positive. Can anybody maybe suggest why that's the case? Why would one be neg and one be positive, even though they're both in the same direction? William? Good. Basically, they're opposing each other, right? If I'm standing here and replacing pail B, and William, you're standing there and replacing pail C, and I'm pulling the way that pail B is, and you're pulling the way that pail C is, we're opposing each other. It's not so much a negative force indicating that it's to the left or down. It's a negative force indicating that it opposes the other force, the positive force. So we have to make one of them negative. Here's my suggestion for a problem like this. You don't have to do this, but it's my suggestion. Redraw it. Let's pretend we have tire A right here. Let's pretend we're stretching up pail B like this. We're kind of pulling it horizontally like this. And pail C, we're kind of pulling up horizontally like this. If that's the case, B would be over here, C would be over here. And if that's the case, then there's a force on pail B this way. And there's a force on pail C this way. That's no more correct than what I have drawn the first time, but it does help me remember that one force has got to be negative and one force has got to be positive. With the way that I have it drawn now, I think it's pretty clear that FB is going to be the negative one, FC is going to be the positive one. Now, if you can spot that just by looking at that original diagram, that's okay. You don't have to redraw it. You need a free body diagram. You need to show all the forces, and I think it's useful to show the forces like this to remind us that we have to make one negative and one positive. If you don't need to do that, that's okay. I think when we do this, we get negative 19.62 on the right side. We're going to divide that by 34, and we end up getting negative 0.58 meters per second squared. Why is it negative? Well, in the free body diagram that I drew second here, the one that I straightened out, it's moving to the left. Now, what does a negative mean over here? Well, it just means, let's look at object A. That's kind of the objective object here, the one that's moving either clearly left or clearly right. Okay, it's going to move to the left as a result of tail B being heavier. So that we're going to say that acceleration is negative 0.58. Although technically, we're only looking for the magnitude of the acceleration here, right? And the magnitude would simply be 0.58 meters per second squared. How is this question similar to what we've done before? Well, it's almost identical to what we've done before, right? Draw all the forces acting on it. F net is equal to the sum of the forces. Solve. How is it different? It's a little bit different in the sense that we got to be careful about the directions more than we have in the past. We've got two directions that appear to be the same, both downward, but we realize when we look closer at it that they oppose each other. One's got to be negative, one's got to be positive. That's really the only difference there. All right? Let's take a look at question number one. Just question number one here at your desks, please. All right, if we're not having any trouble with that question, I want to do another example. This will probably be the last one that we do here today. 3.16 on 179, it says a 3.5 kilogram block is sliding down an incline of 15 degrees. The surface of the incline exerts a force of kinetic friction of 3.9 newtons on the block. What's the acceleration of the block? This one is a little bit more challenging. Okay, this one is similar to what we've been doing, but different still. There's an extra step in this one that we have to do that we haven't had to do thus far. Here's the deal. We have a force of friction acting on the block. We know that force of friction is going to oppose the motion of this block. Which way does this block want to move? In the absence of friction, which way would it move? If friction wasn't there, it would move, good, down the slope. Good. So friction has to act up the slope, right? All right, well, what is the force that acts down the slope? Like, what force is it that pulls it down the slope? Gravity doesn't pull it down the slope. Gravity would pull it straight down this way. The normal force doesn't pull it down the slope. The normal force would push it up this way. What force is it that pulls it down the slope? Rosie? Yeah, it's a mixture of gravity and the normal force. Let's draw this. Just bear with me for a second here, okay? Don't write this down yet. Just watch me. We have a normal force pushing up like this, and we have gravity pulling down like this. This object is going to move left and down. It's going to move down as a result of the force of gravity. It's going to move left as a result of the x component of the normal force. So gravity and the normal force combined will give me the force that acts down the hill, the force that pulls it down the hill. We're going to call the combined gravity and normal force. Remember, I can add forces together in 2 dimensions. When I add normal force and gravity together, I get a force that I call F parallel. I'm going to redraw that F parallel right there. I'm going to make this a little bit shorter, actually. So understand what I've done there. I got two F parallels drawn, 2 red forces drawn, but there's not 2 of them existing. There's only one of them there. I'm just drawing it in 2 different places. I'm allowed to draw it wherever I want, right? I drew it right here, and then I chose to move it over to right there. It is the force that pulls it down the hill. It is the normal force and the force of gravity combined. Now, we just got to figure out what that value of F parallel is. Okay, first of all, recognize that this angle is always 90 degrees. Okay, think about that. F parallel is parallel to the surface, and F normal is always perpendicular to the surface, so F parallel and F normal have to be perpendicular to each other. This angle right here inside this triangle will always be the angle of the hill. I'm not going to go through the trigonometrical and geometrical analysis of that unless you want to question that, and then I will. Okay, but for some of you, it's just going to confuse you. Some of you it won't. Some of you it would. Those 2 angles are always the same. Now, if I want to find F parallel, then I can, over to the side here, say sine 15 degrees is equal to opposite over hypotenuse. And the hypotenuse is the force of gravity. So I'm going to say F parallel is equal to 3.5 times 9.81. That's the force of gravity times sine 15 degrees. Do that math. I should get, let's see here, 3.5 times 9.81 times sine 15. I do that, I get 8.88655 newtons. So if the normal force and gravity combine to pull it down the hill, then I have to find the combined normal force and gravity that I call F parallel. And that's exactly what I just did. So now what I'm going to do here is label this F parallel up here 8.88655. Okay, this is also 8.88655. Doesn't really matter about that one though. I want it drawn up opposite to the force of friction there. So you got this situation on we call it an inclined plane, because physicists have to use fancy terms, right? Okay, most of us would call it a hill. Okay, well, we're going to call it an inclined plane because we want to sound smart or something. It's a hill. It's an inclined plane. When you have one of those problems, you have to find the force parallel. And that force parallel is Fn plus Fg. But not just Fn plus Fg adding scalars, Fn plus Fg adding vectors. To find F parallel, to find the sum of these two vectors, right, the resultant vector, we have to use a sine function. All right, where are we at now? Now it's easy. F net is equal to the sum of the forces. We're going to say F parallel plus FF. Anybody explain to me why I did not put Fn or Fg in there? Why did I only include the two forces at the top, F parallel and FF? Fn and Fg do not cancel out this time. So why didn't I include them? Done? Good. Perfect answer. I did include them. I did. I already included them. This force right here is already Fn and Fg. Okay, I have to include all of the forces acting on this object that don't cancel out. And all the other problems we've done, Fn and Fg have canceled. Now they don't cancel. So I have to include them. But I'm including them together with F parallel. So I'm going to say F net, 3.5 times the acceleration, is equal to, I'm going to say negative 8.88. 655 because it's pulling it down the hill, plus the normal force of 3.9 newtons. And when I do that, I should get negative 1.42. Negative 1.42 meters per second squared. All right? Yep. Oh, you're right. Yep. Yep, you're right. I missed that. 2 significant digits, 3 significant digits, 2 digits. Final answer should be 2 digits. So it would be 1.4 meters per second squared. The only time that I would ever say it's 3 when there's a 2-digit number in the question is if I didn't use that 2-digit number. But I clearly used it here. Thank you. Got it? Hard? A little bit harder. Hey, a little bit harder. The good news is this analysis right here is the same every time. The good news is it's the only difference. All right, if you take away what's circled in black there, how is this question any different than anything else we've done? None. None. It's easy, right? Really, it's easy, except for what's circled in black there. So you just got to make sure that you can do what's circled in black, combine it with what we've done over the last few days, and you're good to go. All right, I would like you for homework tonight to go back to finishing question number, you know what, never mind, don't do number 2. Just do these 2 questions on page 179. These 2 questions on page 179.